In this video, the following topics will be covered: BIRCH, DBSCAN, STING, CLIQUE, and the evaluation of clustering techniques. Clustering a large amount of numeric data by integrating hierarchical clustering and other clustering methods such as iterative partitioning. It overcomes the two difficulties in agglomerative clustering methods. Number one, scalability. Number two, the inability to undo what was done in the previous step. Multi-phase hierarchical clustering using clustering feature tree, balanced iterative reducing and clustering using hierarchies. That is an expansion for the BIRCH is designed for the clustering a large amount of numeric data by integrating hierarchical clustering and other clustering methods such as iterative partitioning. It overcomes the two difficulties in agglomerative clustering methods, scalability and the inability to undo what was done in the previous step. BIRCH uses the notion of clustering features to summarize a cluster and clustering feature tree as CF tree to represent a cluster hierarchy. The structures of the clustering method achieve good speed and scalability in large or even streaming databases and also make it effective for incremental and dynamic clustering of incoming objects. Phase 1, BIRCH scans the database to build an initial in-memory CF tree, which can be viewed as a multi-level compression of the data that tries to preserve the data. It's an inherent clustering structure. And second phase, BIRCH applies a clustering algorithm to cluster the leaf nodes of the CF tree, which removes sparse clusters as outliers and groups dense clusters into large ones. Scales linearly, finds a good clustering with a single scan and improves the quality with a few additional scans. Weakness of this algorithm, it handles only a numeric data and sensitive to the order of the data record. Consider a cluster of end d-dimensional data objects or points. The clustering feature tree, CF tree, of the cluster is a three-dimensional vector summarizing information about clusters of objects. It is defined as CF equals sign n, ls, ss, where ls is the linear sum of the n points, that is, sum of I is equals to 1, then xi, and ss is the square sum of the data points. A clustering feature is essentially a summary of the statistics for the given cluster. Using a clustering feature, we can easily derive many useful statistics of a cluster. Yes, CF tree is a height balance tree that stores the clustering features for hierarchical clustering. By definition, a non-leaf node in a tree has a descendants or children. The non-leaf nodes store sums of the clustering features of their children and thus summarize clustering information about their children. A CF tree has two parameters, branching factor as a capital B and threshold capital T. The branching factor specifies the maximum number of children per non-leaf node. The threshold parameter specifies the maximum diameter of subclusters stored at the leaf nodes of the tree. These two parameters implicitly control the resulting tree size. Given a limited amount of main memory, an important consideration in BIRCH is to maximize the time required for input and output. BIRCH applies a multi-phase clustering technique. A single scan of the data set yields a good clustering, and one or more additional scans can optionally be used to further improve the quality. The primary phases of the BIRCH is phase 1. BIRCH scans a database to build an initial in-memory CFT, which can be viewed as multi-level compression of the data that tries to preserve the data's inherent clustering feature. Phase 2, BIRCH applies a clustering algorithm to cluster the leaf nodes of the CF tree, which removes sparse clusters as outliers and groups dense clusters into larger ones. The clustering feature, suppose there are 3 points 2, 5, 3, 2 and 4, 3 in a cluster C1. The clustering of C1 is given. CF1 equals to, the values are given in the screen. Suppose that C1 is disjoint to a second cluster C2, where CF2 is given as 3, 35, 36 and 417, 440. The clustering feature of a new cluster C3 that is formed by merging C1 and C2 is derived by CF1 and CF2 that is given on the screen. For phase 1, the CF tree is built dynamically as objects are inserted, thus the method is incremental. An object is inserted into the closest leaf entry if the diameter of the subcluster stored in the leaf node after insertion is larger than the threshold value. Then the leaf node and possibly other nodes are split. After the insertion of the new object, information about the object is passed toward the root of the tree. The size of the CF tree can be changed by modifying the threshold. If the size of the memory that is needed for storing the CF tree is larger than the size of the main memory, then the larger threshold value can be specified and the CF tree is rebuilt. Time complexity of the algorithm is O of n, where n is the number of objects to be clustered. Experiments have shown that the linear scalability of the algorithm with respect to the number of objects and good quality of clustering of the data. However, since each node in a CF tree can hold only a limited number of entries due to its size, a CF tree node does not always correspond to what a user may consider a natural cluster. Moreover, if the clusters are not spherical shape, BIRCH does not perform well because it uses the notion of radius or diameter to control the boundary of a cluster. The concerns about this algorithm, then it is very sensitive to insertion order of data point. Second, since we fix the size of leaf node, so clusters may not be so natural. Third one, the clusters tend to be spherical given the radius and the diameter measure. The steps in the algorithm, it builds the CF tree out of the data points. Algorithm scans all leaf entries to rebuild a smaller CF tree, removing outliers and grouping subclusters to layers 1. Thus, step number 3, an existing clustering algorithm is used to cluster leaf entries. User can specify desired diameters. Step number 4, redistribute the data points to its closest centroid of clusters found in step 3. Partitioning and hierarchical methods are designed to find the spherical shaped clusters. Density-based clusters are dense areas in the data space separated from each other by sparse areas. Given data, portioning and hierarchical will likely inaccurately identify convex regions where noise or outliers are included in the cluster. To find clusters of arbitrary shape, alternatively, we may model clusters as dense regions in the data space separated by sparse regions. That is the main strategy behind density-based clustering methods, which can discover clusters of non-spherical shape. How can we find dense regions in density-based clustering? The density of an object O can be measured by the number of objects close to O. DBSCAN, density-based spatial clustering of applications with the noise, finds core objects, that is, objects that have dense neighborhoods. It connects core objects and their neighborhoods to form dense regions as cluster. How does DBSCAN quantify the neighborhood of an object? As a user-specified parameter epsilon greater than 0 is used to specify the radius of a neighborhood we consider for every object. The E neighborhood of an object O is the space within radius E and centered at O. Due to the fixed neighborhood size parameterized by E, the density of a neighborhood can be measured by simply by the number of objects in the neighborhood. How does DBSCAN quantify the neighborhood of an object? Clustering based on density, such as density connected points. The major features are discover the clusters of arbitrary shape, handling the noise, one scan, need density parameters at terminated condition. Several interesting studies are available, DBSCAN, Optics, DenClue and CLIQUE. Note that density-based clusters are monotonic with respect to neighborhood threshold. That is, in DBSCAN, for a fixed min PTS value and two neighborhood thresholds, E1 less than E2, a cluster C with respect to E1 and min PTS must be a subset of a cluster C dash with respect to E2 and min PTS. This means that if two objects are in a density-based cluster, they must also be in a cluster with a lower density requirement. Density reachable means a point P is density reachable from a point Q with respect to EPS. Min PTS, if there is a chain of points P1 up to Pn or P1 equal to Q or Pn equal to P such that Pi plus 1 is directly density reachable from Pa. Density connected means a point P is density connected to a point Q with respect to EPS. Min PTS, if there is a point O such that both P and Q are density reachable from O with respect to EPS and min PTS. Relies on density-based notion of cluster. A cluster is defined as a maximal set of density connected points, discovers clusters of arbitrary shape in spatial databases with noise. The algorithm, the arbitrarily select a point P, retrieve all points density reachable from P with respect to EPS and min PTS. If P is a core point, a cluster can be formed. If P is a border point, no points are density reachable from P and DBSCAN visits the next point of the database. Continue the process until all of the points have been processed. An algorithm continued. DS2 with min PTS at 4 and EPS and A, B, C is shown on the screen. STING is an abbreviation of Statistical Information Grid. It's a grid-based multi-resolution clustering technique in which the embedding spatial area of the input object is divided into rectangular cells. The space can be divided in a hierarchical and recursive way. Several levels of such rectangular cells correspond to different levels of resolution and form a hierarchical structure. Each cell at high level is partitioned to form a number of cells at the next lower level. Statistical information regarding the attributes in each grid cell, such as the mean, maximum, and minimum values, is pre-computed and stored as a statistical parameter. These statistical parameters are useful for query processing and for other data analysis tasks. Shown on the screen, a hierarchical structure for string clustering. The statistical parameters of higher level cells can easily be computed from the parameters of the lower level cells. These parameters include the following: the attribute independent parameter count and the attribute dependent parameters mean and standard deviation, maximum, and the type of distribution that the attribute value in the cell follows, such as normal, uniform, exponential, or none. Here the attribute is selected. The measure for analysis such as price for house of objects when the data are loaded into the databases. And the parameters count, mean, standard deviation, min and max of the bottom level cells are calculated directly from the data. It uses a top-down approach to answer spatial data queries. It starts from a pre-selected layer, typically with a small number of cells. For each cell in the current level, compute the confidence interval. Then it removes the irrelevant cells from further consideration. When finished examining the current layer, proceed to the next lower level. Repeat this process until the bottom layer is reached. Advantages of this algorithm: query independent, easy to parallelize, incremental update, O of k, where k is the number of grid cells at the lowest level. The disadvantages in this algorithm: all the cluster boundaries are either horizontal or vertical, no diagonal boundary is selected. The next one is the CLIQUE, an a priori like subspace clustering method. CLIQUE is a clustering in queue that automatically identifying subspaces of a high dimensional data space and that allow better clustering than original space. CLIQUE is a clustering queues is a simple grid-based method for finding density-based clusters in subspaces. CLIQUE partitions each dimension into overlapping interval, thereby partitioning the entire embedding space of the data objects into cells. It uses density threshold to identify dense cells and sparse ones. A cell is dense if the number of objects mapped to it exceeds the density threshold. The main strategy behind CLIQUE for identifying a candidate cell space uses the monotonicity of dense cells with respect to dimensionality. This is based on the a priori property used in frequent pattern and association rule mining. These steps in this algorithm, it partitions the data space and finds the number of points that lie inside each cell of the partition. Identify the subspaces that contain clusters using the a priori principle. Identify the clusters. First one, determine dense units in all subspaces of interest. Determine connected dense units in all subspaces of interest. Generate minimal description of the clusters. Determine maximal regions that cover a cluster of connected dense units for each cluster. Determination of minimal cover for each cluster. CLIQUE performs clustering in two steps. In the first step, CLIQUE partitions the dimensional data space into non-overlapping rectangular units, identifying the dense units among these. CLIQUE finds these dense cells in all of the subspaces. To do, the CLIQUE partitions every dimensions into intervals and identifies intervals containing at least L points, where L is the density threshold. CLIQUE then iteratively joins two k-dimensional denses C1 and C2 in subspaces, the di1, di2 up to dik and dj1 up to djk respectively. So in the which shares the same intervals in those dimensions. The join operation generates new k plus 1 dimension candidate cell C in space di1 to dik and djk dj1 to djk. CLIQUE checks whether the number of points in C passes the density threshold, and the iteration terminates when no candidates can be generated or no candidate cells are dense. Strength of a CLIQUE automatically finds subspaces of the highest dimensionality such that high density clusters exist in those subspaces, insensitive to the order of records in input and does not presume some canonical data distribution. It scales linearly with the size of the input and has good scalability as the number of dimensions in the data increases. The weakness of the CLIQUE is the accuracy of the clustering result may be degraded at the expense of simplicity of the method. Next is evaluation of clustering techniques. Clustering tendency assessment determines whether a given data set has a non-random structure which may lead to meaningful clusters. Consider a data set that does not have any non-random structure, such as a set of uniformly distributed points in a data space. Even though a clustering algorithm may return clusters for the data, those clusters are random and are not meaningful. Determine the number of clusters. First one, empirical method. Number of clusters equals to square root of n by 2 for a data set of n points. Second one, elbow method. Use the turning point in the curve of sum of within cluster variance with respect to the number of clusters. As third one, cross-validation method. Divide a given data set into m parts. Use m minus 1 parts to obtain clustering model. Use the remaining part to test the quality of the clustering. For any k greater than 0 repeated m times, compare the overall quality measure with respect to different k's and find the number of clusters that fits the data the best. Clustering quality. We have few methods to choose from for measuring the quality of a clustering. In general, these methods can be categorized into two groups according to whether ground truth is available. Here, ground truth is the ideal clustering that is often built using human experts. If the ground truth is available, it can be used by extrinsic methods which compare the clustering against the group truth and the measure. If the ground truth is unavailable, we can use the intrinsic methods, which evaluate the goodness of a clustering by considering how well the clusters are separated. Ground truth can be considered as supervision in the form of cluster labels. Hence, extrinsic methods are also known as supervised methods, while intrinsic methods are known as unsupervised methods. Measuring the clustering quality, Q is good if it satisfies the following four essential criteria: cluster homogeneity, cluster completeness, backbone, and small cluster preservation.